Hello everyone. So today I'm going to just be writing out the example problem that I did in class on Wednesday. This is example problem 4.5 in your textbook. The reason why I'm going to be going over it again is because the Zoom recording wasn't that good of quality. Also, you can see the whiteboard, so I'm just deciding to just go over it one more time, but I'm going to be solving it a little bit differently. So first thing to do is to read the problem and then draw the diagram. So just coming off this, there is a distillation column that is trying to separate ethanol from water. So it's giving you a feed of 200 kilomoles per hour, and it's 30% ethanol. It's a saturated vapor, which is going to be important later on in the problem. It also says that there is a second feed, feed 2, which is 300 kilomoles per hour, and it is 40% ethanol. Feed 2 is also a subcooled liquid, and 1 mole of vapor must condense inside the column to heat up 4 moles of feed 2 to its boiling point. We'll talk about that a little bit later. That's talking about the desired part, so our bottom concentration, our XB, is going to be 2%, and our distillate XD is going to be 72%. The reflux ratio is 1. It's a saturated liquid, the column's operating at 1 atm, and it's well insulated, so that just means that it's under adiabatic conditions. This problem is asking you to find the optimum feed locations, and also the total number of equilibrium stages that are required. Another point of information is right at the beginning of the problem statement that says it is a total condenser, which means when we are counting our steps for the McCabe-Dewey diagram, it's not going to be considered an equilibrium stage, it's ignored. However, the boiler is a partial word boiler, so that will be part of the equilibrium counting, step counting process, which we'll talk more about later. So getting ready to it, here's the diagram. So it's telling you that there's 2 feeds, one is of higher concentration than the other. You can arbitrarily put these 2 feeds in any location you want, and then when you draw the graph, it'll show you which feed needs to be above the other one, or you can assume, since as you're going up the column, the concentration of ethanol is going to be greater as you're moving up, you can just say that assume that the highest concentration feed is going to be above the lower concentration feed, which is right most of the time. So here's our diagram, and let's give a little intro of what it's going to look like. So before, when we were doing one feed, you would have one feed line right here, which comes from the y equals x line. You would have one bottom operating line, and you would have one top operating line. However, now that we have a second feed line, we're going to have 2 of those. So we're going to have one feed line here, one feed line here, our top operating line, and then we're going to have this new thing called the middle operating line. So what these operating lines do is they're a linear equation that describes how the mass is distributed throughout the column in that section. So what I mean by that, here in this section of the column, above feed 2, you're going to have vapor coming in, which will be denoted just a V, and liquid coming down. That'll be L. So this portion of the column from here up is going to behave differently than, say, this portion and this portion. The reason why they're different is because there's a feed that's changing how the mass is flowing. Feed 2 comes in and is going to mess everything up and change what's going in between this middle section. Feed 1 is going to come in and create a completely different type of situation. So there's going to be different operating lines depending on how many feeds. You could, of course, add a third feed, and then that would generate another second middle operating line. But I think for the extent of this class, we might just be seeing only 2 feeds. So here beneath feed 2, we need to have also our vapor, but that's going to be V prime, different labeling system. And we're going to have L prime. This is all just so we can keep track of where we're at in the column. And then on the bottom, it's usually denoted with bars. So the first thing we need to do is plot the lines that we know. We need to plot our top operating line, our feed lines, bottom operating lines. So let's just start at the top. You can start wherever you like. I'm choosing to go over the top. I have the equations already written out for the feed and the bottom. But for the top, I want to go over how you actually find the operating lines in case anyone's confused. So to do that, I drew this red boxed envelope around the top of the column. And then you're just simply doing a mass balance. So in equals out. So coming in, we have our vapor. That's all that's coming in. Coming out, we have our distillate, and we have our liquid. If you can't see that, we have our vapor coming in, our liquid coming out, and our distillate coming out. So the next step is to do the exact same thing, but with a most volatile component. And then solving for y. So to solve for y, you just divide out the v, distillate over v. And that's it. That's how you get your pretty much any operating line, regardless of the section of the column. So you can solve this in terms of, typically I think you'll see this in terms of L over V. To do that, you just take this equation. So you want to plug in for distillate. So it's going to be equal to V minus L over V XD plus just L over V. Write the last term first. And there you go. That should be the equation that you guys recognize from the book. Another useful equation that I prefer is in terms of reflux ratio. Your reflux ratio is equal to your L over D, how much liquid you're putting back into the column, versus how much you're taking out. So to do that, you need everything in terms of D and L. So you just come back to this original equation and substitute in for V. Do that, get, and then all you're going to be doing is just dividing everything by D. And you have your equation in terms of reflux ratio. Okay, there you go. So we need to now plot this line. So if you're plotting any linear relationship, you need 2 different sets satisfied, 1 of 2 different sets to be satisfied. You need to know 1 point that needs to be given, regardless, and then you need to know either 1 more point, so a total of 2 points, or you can do 1 point and a slope. So that's what you need. For the bottom operating line and the top operating line, the first point's already given. It's always going to be that whatever your XD or your XB, in this case XD, whatever is given as your distillate composition, you go to the y equals x, which is the green line here, you go to your y equals x line and start there. So to do that, we'll go to 0.72. So that's 1 point. So then what we're going to need is we're going to need either the slope or the intercept. You can do anything you want here. So we know our reflux ratio that was given as 1. So if we plug that into here, we can get that our slope then is equal to 1/2. We can also find our y-intercept, which is just x equals 0. And that's going to be 1 minus 1/2 times our x distillate, which is 0.72, which would just be equal to 0.36. Okay, so you can choose either or. You can go down, go up 1 and to the right 2, or you can just go to the intercept. I'm just going to go to the intercept for this one. It's going to be equal to 0.36. That's good enough. Okay, so now we have our top operating line drawn out. So now the first thing we need to do next is we can go across and do our feed line. We can do our bottom operating line. Let's just go across and do our feed 2. So feed 2 is telling us that it is a subcooled liquid where 1 mole of vapor must condense inside the column to heat up 4 moles of feed 2. So our Q right here, this is where we're going to get introduced into a little different concept than normal. So our Q's are defined as this. The Q can be defined as the liquid below minus the liquid above over our feed. So in this case, it's going to be feed 2. Illustration of what's going on at this plate where feed 2 is being fed into. So we have our tray. We have our feed 2, which is going to come down because it's a subcooled liquid. We have a liquid coming down. We have a vapor coming up. Liquid coming down. Vapor rising. This is our V. If we look over here at the column, we're at this section. So the subscripts are going to change. We're going to have our V bar below. We're going to have our L. And then we're going to have our L bar. But there's another component to this. It mentions in the problem statement that for every mole, don't want to get this wrong. So for 1 mole of vapor must condense inside the column to heat up 4 moles of feed. So what's happening is you have vapor coming up. It's getting subcooled. It's getting cooled by the subcooled liquid, and it's condensing. We're going to call that C, the amount that's being condensed. So what we care about up here is we care about the L below, which is this L prime. This is L below. We care about the L above, which is this L. And then our L prime then is going to be equal to our F2 that's coming in. Our condensation is contributing to that. Plus we initially have the L above it. So our L prime is going to be equal to F2 plus C plus L. So we can then bring this Q equation down and say L below is going to be our L bar, which is our L prime, which is F2 plus C minus our L above, which is just going to be regular L, over our F2. We need to figure out, well, these L's will cancel, but we need to figure out what this C is equal to. From the problem statement, it says that 1 mole of vapor will condense for every 4 moles of feed. So what that's going to equal is the amount of condensate that we're going to have is going to be equal to 1/4 of the flow rate. Okay, so that just goes into here now. And that Q will be equal to F2 plus 1/4 of the feed, which will just equal 5/4. So that's our Q. What was the point of this again? It was to plug it into this feed 2 equation right here. So let's do that. We have then that our Q, or Y, our feed line is going to be equal to 5/4 over 5/4 minus 1. We know what our composition is. Our composition for feed 2 is 0.4. So again, like I said previously, in order to draw a linear line, we need either 2 points or 1 point in the slope. As with the top operating line, we are going to go to the y equals x line for the composition. So our composition for this is 0.4. So we're simply going to go up here and go to 0.4. Oops. Okay. Then we need either the slope or we need the intercept. So what we can say is, well, let's see what the slope gives us. It's going to be equal to 5. Sorry. So our slope will be equal to 5, or our intercept at x equals 0 will be solving this, which will be 0.4 over 1/4, which would be times 4, which would be 1.6. Okay, so we can now use either one of these ones. If I go to the graph, I don't have 1.6 on there. We could just do 5, so you can just pick whatever you want. I think what I'll use is, it's negative 1.6. Sorry about that. So we can go to our graph. We can either go all the way down and create a new sheet of paper, or we can just do a slope of 5. So the slope of 5 is equivalent to just going up 2.5 and going over 1/2. So 1, 2.5, and going over 1/2. So it's about here. So somewhere about there. Let's draw that. I'm trying to use lines here so we can get as accurate of a step counting as possible. So it's going to be the intersection of this half. So it'll be here. We'll start at 0.4, and we're going to be going all the way up to here. Okay, so now we have our feed line. These are going away. So that we don't get confused, we're going to start labeling. Here's our top, and here's feed 2. Okay, perfect. Now what we need to do is we need to keep going. So I guess we can do our feed 1. Something that it tells you, however, in feed 1 is that it is a saturated vapor. Now in the book, it derives the fact that if you have a saturated vapor, your Q is equal to 0 for a saturated vapor. If you have a saturated liquid, your Q equals 1, which means your slope then goes to infinity. And for this, you also get a slope equal to 0. So that's easy enough. We have a point and we have our slope for our feed 1 operating line. So for our feed 1 operating line, we need to go to where the component y equals x at 3. So it's going to be about here. And then we have a slope of 0. So from there, we just draw a 0 slope at y equals x equals 3. Okay, so there is our feed 2 operating line. I'm sorry, feed 1. So this is feed 1. Okay, almost there. So the next thing we have to do then is keep going, our bottom operating line. So if we look at our bottom operating line, we have a point, we have xb. That's given. So if we come back over here, we know that our xb is equal to 0.02. So that's going to be about, very small, about there. So we have 1 point. Now we need either the slope, which that's not known, or we need an intercept, which is also not known. So what we're going to actually do here is we're going to skip the bottom operating line creation, and we're going to go straight to the middle line. So creating the middle line is the exact same process as when we were creating the top line. So for that, we're going to need to draw an envelope, but we're going to want to make sure that we include one of the feed lines and not include the entirety of the column. So we have two options. We can either do this way, around the distillate and covering feed 2, or we can go around the bottoms. So what the book decided to go over the top. So for the sake of being different, I'm going to show you guys how to do it using the bottom. Either way, if you're doing it around the top half of the column or the bottom half of the column, you'll get the same answer. So I'll show you that right here. So for the middle operating line, let's see here. I'm just going to do it over here. You draw an envelope around it, and you're just going to be doing a mass balance. So what's coming in? You've got feed 1 coming in. You have L bar coming in. And that's it. Coming out, you have V bar, V prime, and you've got your bottoms coming out. Now, the reason we're not including the V bar and the L bar is because we need to take the envelope of including the feed. So to include the feed, we're going slightly above it, which means we're in this V prime and L prime phase. So the subscripts are going to be V prime and L prime, not V bar and L bar. So we have our overall mass balance for the middle section. Just like the top, we'll take a most volatile component mass balance, which will be simply F1Z1 L prime X, V prime Y, plus VXV. Solving for Y, we get Y is equal to Z1 L prime X minus VXV. Everything gets divided by V prime. So let's clean it up. Y is equal to L bar over V, L prime over V prime times X plus F1 Z1 minus VXV over V1. So again, as I said earlier, you need 2 points or a point and a slope. We have a point right here. At the intersection of these two lines, that is going to be 1 point for the middle operating line, because we know that it must intercept the feed line, and it also must intercept the top operating line. So we have 1 point. All we need now is a slope, or we need an intercept. So looking at the equation, the slope, we don't have that. Looking at the intercept, we also don't have that either. But what we can do is we can make the assumption that it crosses this y equals x line, the green line. If we make the assumption that it crosses the y equals x line, we can solve for 1 point. We're saying that y equals x. This gets translated to y equals plus all this down here. So solving for y again. Over and then just distributing the v bar. V prime, excuse me. So we get that our y equals F1 Z1 minus our bottoms times our x bottom composition over the difference between V prime minus L prime. So what was that? That is where we intercept the y equals x line. We have our bottom concentration, we have our feed, and we have our z. We do not have this, however. So let's try to solve for that. In order to solve for that, we can go back to our middle operating line. So to solve for our middle, we can go back to our overall mass balance. So doing that, I'm going to bring it down here and solve in terms of V minus L. So let's solve in terms of V minus L primes, simply going to be equal to our feed 1 minus our bottoms. So we can plug that into here. If we do, we get that our y equals all this. Now this, of course, makes the assumption that your middle operating line, which is what we're solving for right here, is going to cross the y equals x line. If it's a situation where your feed is the same as your bottom flow rate, you get 0 right here. And if you get 0 right here, that says that you will cross the y equals x line at infinity. What that means is it means that you are parallel. It means that your middle operating line is going to be parallel to this y equals x line. So from there, as you know, y equals x line, the slope is equal to 1. So you then know that your slope of your middle operating line is 1. If your slope is 1, and you have this point right here that I mentioned, then you're good to go. You can just use the slope to go down 1, over 1, to left 1, and then figure out what the line looks like from there. But since our f1 does not equal b, or at least we don't know that at this point, we're going to have to figure this out. So to do this, we now need to do an overall mass balance for the entire system. So to do that, zoom out again, and look at our column. So I'm going to block all this off and do an overall for the entire column. So if we're doing an overall for the entire column, we know that f2 is coming in, f1 is coming in, and that's the only things that are coming in. We have that must be equal then to our distillate flow rate plus our bottom. Again, we know 2 of the 4, so we need another equation, and that one's just going to be the most volatile component equation. Okay, 2 equations, 2 unknowns. You can solve for it. When you solve for it, you end up getting that your bottom flow rate is going to be equal to 257. Okay, once you have that, because you can do that by just simply solving for in terms of D and plugging in for B, or vice versa. You have the feed, you have everything here, except for 2 unknowns, and you have 2 equations. The next step from there would be to plug your B back into here, because everything else is given. So what you get is you get y is equal to, our f1 is 200, z1 is 0.3, there's our bottom times our bottom concentration, over 200 minus 257. This gets you is negative 0.962. So what was this again? We solved the y value. This y value is the value at which it intercepts the y equals x line. So we can now plot this graph. So the value that it crosses the y equals x line at is negative, about negative 1. All right, so what I did here was I decided to draw about approximately 0.96 in length square. So starting from the 0 point here, going negative 0.96 and going another negative downward 0.96. This point right here will be the intercept of the y equals x line with this point. So remember, we just solved for the point here, was kind of just the intersection that's kind of given. You don't really need to figure out what it is numerically. You just need to figure out how to assemble the slope, or how to assemble a line. So we know we have a point here, and we have a point here that intercepts where the y equals x line. So let's go ahead and draw that line now. All right, that's good enough. So there we go. We have our middle operating line now. Perfect. So we are almost done. We assembled this middle operating line because we know it's going to intersect this point right here. We also know that it is going to intercept the y equals x line at some very negative value over here. Now we have our top line, we have our feed 1 right here, and our feed 2. We have our middle operating line. All we need now is our bottom operating line. Now to do that, you don't necessarily need to calculate any values. All you need to do is you need to go to where x equals 0.02 on the y equals x diagram, which I made earlier, and just go to this intersection, because you know that it has to intercept where your feed 1 crosses your middle operating line. So your bottom operating line, instead of doing any math or algebra, you can just simply draw a line. So we know that our bottom operating line is about here, I guess. So about here to here. Right, so now you're done. You have your Cave-Thiele diagram with your bottom operating line, your top operating line, middle operating line, and all your feed lines. So there you go. What I'm going to do now is I'm just going to clean up this diagram a little bit because it's a little messy. Because now what we have to do is we have to start counting our steps. So all I'm going to do is I'm going to make the lines a little bit cleaner. All right, so here we have our McCabe-Thiele diagram with the lines cleaned up. We have our bottom operating line right here. We have our feed 1. We have our feed 2. We have our middle. It's right there. And our top. Because it was asking for the location of the feeds as well as the number of equilibrium trace. So to do that, we need to do some step counting. And remember, what you do for step counting is you go to you start at either your distillate or you start at your bottom's concentration. For this one, I'm going to start at the bottom. So what you do is you take your bottom X concentration and you go up to where you hit the vapor equilibrium curve, and then you go to the right. You stop at your bottom operating line, and then you go up, and then you go over, and you follow this throughout the entirety of the curve. What I'm going to do is I'm going to try to keep it as straight line as possible. So I'm going to start using straight lines and see how good I can get this. So you can see I started here at my X bottom concentration of 0.02, or approximately that. I go up to the vapor equilibrium. I went to the vapor equilibrium line, and then immediately did a right angle over to the right to the bottom operating line. Then moving in another right angle, you move directly up to the vapor equilibrium line, and you stop there, create another right angle, go all the way to now you're going to be intersecting the middle operating line, create another right angle, go up to the vapor liquid equilibrium, another right angle, go across, make another right angle, go up, and you keep following this making right angles until you get to here. So look at this portion closer to the distillate concentration. You can see I created lines that are a little bit more accurate, that are closer to the 0.72, and I made lines coming out this way and coming down this way. So when you cross it, that's when you stop. So if you notice right here, this last leg, this last step going up, it crosses your distillate concentration. So you stop. As soon as you cross, either for the opposite, if you're going down, as soon as you cross your bottom concentration, you stop, or when you go to the point where you cross your distillate concentration, you also stop. So from there, we're going to stop, and then now we're going to count the steps and how many equilibrium trays we're going to need. So come to the bottom, it would be 1. However, it's not 1 because in the problem statement, it said that it is a partial reboiler, so this is going to be your partial reboiler, is your first stage. Then, walking up, we have 1, 2, 3, 4, 5. Now here's where it gets tricky. It doesn't meet right there for the 6th one. You are crossing your distillate composition, your 0.72 line, before you get to the equilibrium line. So it's actually about, the way I have it drawn is about 3/4 of a tray. The way the book has it, it has it as 5.5, but hey, we're close enough. So what you have here is you have that you're going to need 5.75 equilibrium stages plus a partial reboiler. So what was that all to say? That was all this work, all the rigorous mathematics and graphing was all to say that if you had an incoming feed 1 and incoming feed 2 of these compositions and these phases coming into a distillation column at these settings, and you wanted a distillate of purity as high as 0.72%, 72%, and you wanted residue as low of quality in ethanol as 2%, then you would need this. So the whole thing was design a distillation problem. So if you're going to design a distillation column, well, you need the column to have this many stages, so you can't have 5.7, so it would be 6 stages, plus a reboiler. But we're still not finished, because the problem statement asked where you put these feeds. So let's go back to the graph. Here's feed 1. Here's our line for feed 1. It is within this section. It's within this first step. So your feed 1, your lower feed, needs to float into the first tray. Now looking at the second one, you can barely tell, but it's falling into this second one right here. So your second feed needs to flow into the second tray. So if you're drawing this distillation column, what it would look like, we'd have 1, 2, 3, 4, 5. That's 6th one. Just to make sure that you get to the necessary conditions, you would have feed coming into here and a feed coming into here. So this is what your overall designed distillation column would look like. Okay, hope that helped. If you have any questions, if I made an error, something was unclear, please feel free to reach out to me and I'd be happy to answer any of your questions. Thanks for watching and have a great day.